All right. Hello, UC Irvine. Let's do this. So good evening, everybody. My name is James Bullock, and I'm Dean of the School of Physical Sciences here at UCI. And it's my great pleasure to welcome you all to the 8th Annual Reines Lecture. It's a really wonderful audience here tonight, filled with esteemed alumni, supporters, and friends from all over. And we're thrilled to have you join us tonight to hear from Nobel laureate Dr. Andrea Ghez. This lecture is hosted by the Physics and Astronomy Department here at UCI, and it owes its success to an unwavering dedication of a special committee of faculty. So a big thank you to Professors Aaron Barth, Claire Yu, and Laszlo Bardozzi. And I'd also like to thank the staff, the many staff who've really put in countless hours to make this happen for you tonight. Yeah, thanks. Now, many of you are regular attendees of the Reines Lecture, and you've become accustomed to an exceptional public science talk from really a giant in their field. We have a legacy of Nobel laureates coming here and just giving fantastic talks. And every year since its inception, it's been our dedicated mission to make sure this is free and accessible to anybody who wants to come. And we really want everyone to come who has an interest. And so, for example, tonight we have many students from local high schools and middle schools. If you're from a high school and middle school, raise your hand. Where are we coming from? That's great. And I'm sure we're hopeful that all of you will be inspired by Dr. Gez's talk tonight. And who knows, maybe one of you will come back and give us this talk in a few years' time. Now, how do we bring this event to you? How do we pull off this free event? Well, it's brought to you by the Frederick Reines Fund, the School of Physical Sciences Dean's Excellence Fund, and the Department of Physics and Astronomy. In addition, I wanted to sort of mention, in particular, Professor Jonathan Fang has generously contributed some of his own unrestricted research funding to make this happen tonight. And so I want to thank Jonathan for that. And moving forward, we really are dedicated to keeping this free. Some of you have donated. We're using the QR code when you walked in the door. There's a way, if you feel like you have the means to give back to enable this to happen. And if anybody feels like they want to help us make this happen in the future, please reach out to me and talk to me, because we really want to make this accessible. It's an opportunity for the community to hear from amazing intellectuals from all over the world. So before introducing Dr. Ghez, I wanted to take a moment to reflect on the legacy of Fred Reines. He's, of course, best known for his groundbreaking discovery of the neutrino, which earned him the Nobel Prize in Physics in 1995. Now, the idea of the neutrino has been with us since the year 1930, when renowned physicist Wolfgang Pauli proposed it to explain missing energy from a radioactive decay. And in order to explain this mystery, in order for this to work, the neutrino had to be incredibly weakly interacting, such that it could travel all the way through the Earth without touching anything. And therefore, how do you detect such a thing? Hans Bethe, another famous physicist, famously stated that there is no practical possible way of detecting the neutrino. And to up the ante, Pauli himself bet a case of champagne that nobody would ever detect one. Enter Fred Reines. Fred and his colleague Clyde Cohen set out to do the impossible, and ultimately they were successful in detecting the neutrino outside of a nuclear reactor. When asked why he was motivated to do this thing, to find the unfindable, Fred Reines is quoted as saying, "Because everybody said you couldn't do it." That was our founding dean. And I believe that unwavering drive to do what is said to be impossible is still with us to this day and inspires many of us to keep searching and working hard. So tonight, on to tonight's speaker. Andrea M. Ghez is a professor of physics and astronomy at UCLA and holds the Lauren B. Leichtman and Arthur E. Levine Chair in Astrophysics at UCLA. She earned her BS from MIT in 1987 and her Ph.D. from Caltech in 1992. She became faculty at UCLA in 1994, and she leads UCLA's Galactic Center Group, which is known internationally for pushing the frontiers of high-resolution astronomical imaging technology. This is a really special night for me and for the University of California, Irvine. As many of you know, I'm an astronomer, and what you may not know is that astronomy is an incredibly close-knit group of people in the University of California system. And one of the reasons is we have the University of California Observatory system, which enables astronomers from every UC campus to have access to some of the best telescopes in the world. So we all know each other and we benefit from each other's expertise. As an example, Irvine's own emeritus professor Gary Channon played a key role in the success of the adaptive optic systems at the Keck telescopes, and this was a key technical breakthrough that Dr. Ghez has used and continues to use to advance her research in her own ingenious way. And of course, many of us have benefited from Dr. Gez's own research and leadership in our own research programs here. So it's a really great, fantastic thing to have her here today, representing the University of California. In 2020, Dr. Ghez became the 4th woman in history to be awarded the Nobel Prize in Physics. This prize recognized her independent discovery of a supermassive compact object at the center of the Milky Way. And we all know what that is. It was a black hole, millions of times the mass of the sun. Her work on the orbits of stars at the center of the galaxy has opened a new approach to study black holes, and her research is currently focusing on using this approach to understand the physics of gravity near black holes and understanding how black holes affect galaxy formation in general. Dr. Gez's accolades include the Crafoord Prize in Astronomy, of which she was the first woman recipient, the Beckerian Medal from the Royal Society, the Annie Jump Cannon Award in Astronomy, the Newton Lacey Pierce Prize of the Astronomical Society, and a MacArthur Genius Fellowship. She's a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. In addition to these remarkable achievements, Dr. Ghez is deeply committed to science communication and fostering diversity in STEM fields. She believes that as a Nobel laureate, she has a responsibility to encourage the next generation of scientists and is dedicated to inspiring young women especially to enter the sciences. And finally, and on a more personal level, I've had the great pleasure of knowing Andrea for a number of years. I won't tell you exactly how many, but I will tell you this. I regard her as an inspiration, a real mentor from the very beginning, and these days really a friend. And so it means a lot to be able to introduce her. Please join me in welcoming Dr. Andrea Ghez.
Well, thank you. That was a very lovely introduction. I'm really delighted to be here this evening to share the journey that I've been on for the last 30 years. It all began when I first joined the faculty at UCLA. And I today think I have my dream job because I'm part of the University of California, where the field of astronomy and astrophysics has the privilege of being part of this incredible collaboration that owns and operates the largest telescope in the world. So discovery is quite easy when you have the best tools. And I was interested, as a young faculty, in developing a new and different way of using this telescope. And I was thinking that I had a good question that would perhaps get me tenure, which is there a supermassive black hole at the center of our galaxy? And at the heart of that question is really the question of whether or not these exotic objects do exist in the universe. Now, it's been quite a journey, and it began a long time ago, and I really want to give a huge shout out throughout this talk to my collaborators. It's an unusual project that's gone on for 30 years, and on my left are 2 senior faculty that I've had the pleasure of collaborating with for 30 years, and on my right, on the right of the screen, is my very first grad student. You can tell this is an old picture because I'm in the middle. And it's at a time, this is when we first went up to the summit to begin this project. But I also want to mention, for the sake of the students, this was also soon after I had submitted the very first proposal to do this work, and it was turned down. It was turned down because they didn't believe that actually this project would be successful. It's where I truly embraced my favorite expression, which is every challenge is an opportunity. And at that time, I learned the importance of convincing your colleagues up and down the UC campuses that what you have in mind will really work, because they have control over who's going to get the nights. Today, we're a much larger collaboration. We're a collaboration of about 24 people that pursues this. Not only have I had students, but today those students are now professors who bring their own grad students and postdocs to this collaboration. And today we serve not only as scientists doing this kind of work, but also as leaders trying to get the next generation of instruments on this fabulous facility. Okay, so to begin the lecture on black holes, it seems appropriate to ask the question, how do you observe something you can't see? Because black holes, by definition, are objects whose pull of gravity is so intense that nothing can escape it, not even light. So the story I'd like to tell you this evening is how we've been able to discover a supermassive black hole at the center of our galaxy. And this has provided us not only with the best evidence to date that these exotic objects really do exist in the universe, but a wonderful laboratory for understanding how gravity works near these supermassive black holes, and how these black holes affect the formation and evolution of the galaxies that they reside in. Okay, so we're off, and it seems important to define what a black hole is. So it seems appropriate to show you a blank slide. While black holes require relatively exotic physics to describe, the way I would like you to think of a black hole this evening is an object whose mass is confined to 0 volume. So despite the fact that we're going to discuss things that are supermassive, they have no finite size. And I'm going to get to what I mean by supermassive in a moment. So if you think about, I'm not going to do much math in this talk, but I'm going to just briefly. We're going to talk about, or think about for a moment, density, which is mass divided by volume. There is no volume that our formalism provides, so density goes to infinity. And in physics, anytime you have a quantity going to infinity, we call it a singularity, which is like a big giant red arrow that says you do not have the description of the physical world correct here. And that actually is why so many physicists and astrophysicists are interested in black holes, because they really represent the frontier of our understanding of the way the world works. This breakdown comes because we don't know today how to make two separate fields work together that are necessary to explain what black holes are. So the field of quantum mechanics, which is the description of things that are very small, on the one hand, and then on the other hand, the theory of general relativity, which is what Einstein is so famous for, and it's the description of things with lots of gravity. So black holes are both, and today we don't know how to bring these things together. Okay. But for this lecture, we can ignore that little detail. Because we can talk about a finite size that is incredibly important to the concept of black hole. This is known as the Schwarzschild radius. Popularized, or it's popularized by Star Trek with the name of the event horizon, the last point at which you can get light can escape from the black hole. So in fact, we can't get information from inside this scale. This scale is also important because every object has a Schwarzschild radius associated with it. And why that's important is because if you can get a mass down to the scale of its Schwarzschild radius, gravity wins. Gravity overcomes all other known forces and forces that mass to become the infinitesimally small object known as a black hole. So you can become a black hole, your neighbor can become a black hole, anything you'd like to turn into a black hole. For me, it would be my cell phone. Well, it is a black hole. Okay, you just need to figure out, there needs to be a process to get the object down to that tiny, tiny scale. So it depends only on mass. So let's think about some objects that we might turn into black holes. So if we could take the Earth and scale it down to the size of a sugar cube, it would become a black hole. Now, let's scale up. If we could take the sun and squeeze it down, I'm sorry, I had to put UCLA here. I should have put Irvine, but they're roughly the same scale. It would become a black hole. Okay, so in a sense, fundamentally, the proof of a black hole is showing that there's a mass inside its Schwarzschild radius. Okay, so a lot of mass inside a small volume is the name of the game. So before we get to the work, let's also think about where black holes turn up in the universe. And there's two categories of black holes, and they so beautifully demonstrate how science works. So the first form are what I'm going to call the little black holes. They're actually quite large. They're about 10 times the mass of the sun. And people thinking about theory anticipated that the most massive stars in our galaxy, those that start their life off with roughly 30 times the mass of the sun or larger, would end their lives in a very dramatic explosion. And this is known as a supernova. And there's all sorts of interesting things happening and that we can get from supernova on the outside. But what I care about is on the inside. So the anticipation is at the end of these stars' lives, the outer layers go shooting off. In other words, gravity loses. But in the inner part, in the core, gravity wins and forces this object to become the infinitesimally small object known as a black hole. I'm going to call these ordinary mass black holes, as if there could be something exotic like this called ordinary. But they were the things that were anticipated. And today we have beautiful observational evidence that these things exist. The most recent example of this is the gravitational wave detections that have, again, emphasized that these things really do exist in the universe. Okay, so it's actually the latter, not these black holes that I care about, but rather what we call supermassive black holes. And so as you might imagine, they're much more massive than these ordinary mass black holes. These things are 1 million to 1 billion times the mass of the sun, so much, much larger than the small ones at 10 times the mass of the sun. We think these black holes reside at the center of galaxies. In other words, one supermassive black hole per galaxy in the middle. So this is a picture, a famous picture taken with Hubble Space Telescope that and almost everything in this picture is a galaxy which has roughly 100 billion stars. So a radically different scale than the last image that we were looking at, where we were looking at a single star. We're going to, in a moment, zoom into the galaxy that's up in the top left that looks like a spiral galaxy. So galaxies are flattened disk-like structures. There's absolutely nothing in this image that suggests to you that there's a supermassive black hole. What we see here, which is a picture taken at optical light, what your eye detects is mostly from the starlight. So it's actually when we go to radio wavelengths, which is closer to where your cell phone works, that we see phenomena that's quite energetic from a small fraction of all these galaxies. Roughly 10% of these galaxies are what I like to call the prima donnas of the galaxy world. And what astronomers call them are active galactic nuclei, because their nuclei, or centers, are very active. So what we see emanating out from the center of these galaxies are these jets. And the jets move incredibly fast, and we can measure that. And that suggests that there's this powerful central engine that powers these jets. So that's thought number one. Thought number two is that at the core, there's light that doesn't look anything like starlight. So it was hypothesized that this is matter in these galaxies falling through the event horizon. So you can think of this light as basically watching the black hole feast. So I like to think big Thanksgiving feast. These hungry beasts were watching the dining habits of these guys. Okay, but all of this is pretty indirect, but nonetheless, why people started to think about the possibility of a supermassive black hole at the heart of galaxies. Started with these exotic ones. but quickly moved to the concept that perhaps all galaxies harbor supermassive black holes, and that they would be lurking or stealthily at the centers, or you can think of them as black holes on a diet. There's nothing accreting, see, they don't light up. Okay, so if we could get outside our own galaxy and look back, this is very much what our own galaxy would look like. We live roughly halfway out from the center, and almost any way we can describe the galaxy is more extreme. So we can think it's extreme astrophysics at the center of the galaxy, exactly where we're looking for this supermassive black hole. So we'll, as you'll see, we not only discover the black hole, but a lot of really interesting astrophysics. Just to give you a sense of the fact that we kind of live in the calm suburbs and are looking downtown at a very exciting place, you can look at the density of stars. The density of stars at the center of the galaxy is 1 billion times higher than where it is in our solar neighborhood. Okay, so it's an interesting place, the center of the galaxy. And the plus of looking for a supermassive black hole at the center of our galaxy is it's the closest example of a center of a galaxy that we'll ever have to look at. The next closest galaxy is 100 times further away. So that's a pro. Like in life, for every pro, you often get a con. Now, what's the con in this case? The con is we live in our galaxy. And remember, it's a flattened disk-like structure, so we have to look through everything that the galaxy contains to see what's going on at the center of the galaxy. Now, this is a beautiful photograph on the side of Mauna Kea, which is where the telescope is in Hawaii. You see the plane of the galaxy. So that's that white swath going through the plane. That's all the stars that reside in the, not all of them, but many of the stars that reside in the center, in the plane of the galaxy. And hopefully you'll also notice a lack of light running through it. And that's because of all the dust that resides in the galaxy. I'm thinking, how much smog do you guys have down here? In LA, we have a lot of smog, so we get a firsthand experience of what that means. On a smoggy day, you can't see very far. And the smog on a smoggy day is actually really is caused by dust. And it has very similar properties to the dust in our galaxy. So dust blocks light that has a wavelength that's comparable or smaller than roughly, than the size of the dust particle. So you can't see the center of the galaxy at optical wavelengths where your eye detects. So we have to do something else. So key to all of this work has been the advent of detectors that are sensitive to light in the infrared, just longward of where your eye detects, where your TV remote control works. So in fact, what UCLA has been very focused on is the development of infrared technology to use on this telescope that everyone within the system benefits from. Okay, so we want to prove that there's a supermassive black hole at the center of the galaxy, and so we're inward bound. We want to see the stars that are as close to the heart of the galaxy as possible, and we want to measure the gravitational influence of the black hole on the things around it. So in particular, we're going to measure the motions of stars, and these stars orbit the center of the galaxy for the same reason that the planets orbit the sun. It's the gravitational pull. And like in the planets, if we could measure, well, we can measure the orbits of those planets, and each planet will tell you how much mass is inside its orbit, and the size of the orbit tells you, well, the scale that mass resides in. And so that hopefully communicates why you want to get as close to the heart of the galaxy as possible, because you want to confine that mass to a small volume. Oh yeah, I'm going to share again for the young people in the audience. The original concept of this project was 3 years long, and we weren't thinking about orbits at the time. We were just thinking about measuring how fast things move. And things on short orbits, which is what happens in the middle, should move faster than the stars at larger radii. And it turns out this works so well that we moved way past that simple 3-year project, which was turned down, to do the full orbits. And the full orbits are a much more robust way of figuring out the answer, as I'll share with you later on. Okay, so we want to see these stars. Actually, we want to discover these stars in the first place. And so in order to see these things, having a large telescope is absolutely key to the story. So we're in campaign season, so I'm going to share there are 2 campaign promises of large telescopes. And the 2 campaign promises is that the larger your telescope, the fainter the objects that you can see. So you can see faint things, which correspond in astronomy and astrophysics to things that are distant. So if you want to understand the origin and evolution of the universe, a big telescope is very helpful. And that mode, when I talk about big, I'm really describing the size of the primary mirror that collects the light. And you can think of that as like a rain bucket. The larger the aperture of your bucket, the more rain you're going to collect. So that's what we're thinking about in this first promise of looking at being able to see really faint things. Turns out I don't care about that aspect. I care about this second promise, which has actually been much harder to achieve. So with larger telescopes, in principle, you should be able to see more detail. And the analogy I like to give here is if you think about the painting technique of pointillism, where you paint with individual dots, the closer you step towards the painting, the better your ability to resolve the individual dots. So having a large telescope, in principle, allows you to resolve the dots on the painting. So you can't get closer, but you can have a bigger telescope to give you more resolving power. And I keep saying we have the largest telescope in the world. These are 2 of them. And how big are these telescopes? So the mirror is 10 meters, and to give you a sense of scale, 10 meters is like the width of a tennis court. And in fact, the University of California came up with a really innovative new design for these telescopes to get to that scale, these mirrors. So it's not one big hunk of glass, but 36 hexagonal segments, very closely, carefully aligned, which is actually what Professor Channon, who Dean Bullock mentioned in the introduction, did so well. He's really responsible for that incredible alignment. We could not do our work, this second piece, without him. Okay, so before I get into the details of how we've achieved this second thing, I'd like to share with you a little bit about why we put this in Hawaii. So this is up on the top of Mauna Kea. If this were a slightly smaller audience, I would ask you why Hawaii is such a premier place for building telescopes. And I would start with my joke. It's a great place to go on vacation. But that's not why we build it there. But it definitely also highlights, I mean, if you think about a place to go on vacation, which is in Hawaii, you think about the tropics, that it's wet and moist. But that's not what astronomers like. Astronomers want really dry climates. So it's really important to, and the way we achieve this in Hawaii is by going up to the summit. So up at the summit of Mauna Kea is about 14,000 feet. So you're high up. In fact, most of the clouds, most of the weather hangs out at about 10,000 feet. In fact, you can see the inner island flights flying by below you. Getting to high altitude is important in terms of the weather. And in fact, getting through most of the atmosphere. Turns out the atmosphere is definitely a problem, and getting to these high elevations is key. Now, you might also think, if you think about Hawaii, Hawaii is a bunch of volcanoes. That's what Hawaii is composed of. So some are active. That's Kilauea. You don't want to build your telescope on an active volcano. And according to the geologists, and we have to trust them, Mauna Kea is a dormant volcano that shouldn't go off for another 1,000,000 years. Now, the second, or another aspect of why Hawaii is such a powerful place to build telescopes is that it's in the middle of the ocean. So we do still have to struggle with the atmosphere. So you'd like the atmospheric flow to be as smooth as possible. So according to the atmospheric scientist, big bodies of water create very smooth airflows. So you'll notice, if you think about where telescopes are located around the world, you find them on tall peaks next to big bodies of water. So that's why you see a lot of them in Chile, in the Andes, in the Canary Islands. They have these dual properties, along with a third property, which is you've struggled very hard to get access to faint light. So the last thing you want to do is build your telescope near a big city with lots of light. Okay, so this is one of my favorite pictures showing this problem. So these are high-tech instruments, facilities, they're huge. So you want access to high-tech industry, and yet high-tech, those high-tech industries tend to be in cities or locations that just light up the sky. So there's an interesting tension. And in Hawaii, there's a lot of collaboration that goes on to keep the light pollution low. In other words, if you go there, you might notice that there's a lot of yellow light, so light that only comes out at a very narrow wavelength to protect the astronomical community. Keck is not the only one up there. There's about a dozen telescopes from countries all over the world. The Keck telescopes are the two tennis balls in the front of this picture. Right next to it, what we call the coffee can, is the telescope Subaru, which is built by the Japanese. You have facilities that are up there from France, Canada, the United Kingdom, and then there's an East Asian consortium as well up there. So there's a really international community of scientists that that have built and operate these facilities. So not only has our technology for these telescopes changed over time, but the way we use them has changed. So I thought it would be interesting to talk a little bit about this aspect. Because we've been doing this long, 30 years, we've actually seen a huge evolution. In the beginning days, everybody would go up to the summit. And if you've ever hiked up at 14,000 feet, you know your brain doesn't work very well up there. And just to give you a sense of this, I had a discussion with one of my grad students, the one in that first picture, about what 128 divided by 2 was our first night. This is not the location you really wanted to be doing your best work. And like on airplanes, most movies are quite funny or quite sad. You're a little euphoric. I actually think this is the moment we realized that there was a black hole at the center of the galaxy, or the first hint, and we were euphoric. We were up at 14,000 feet. Around 1998, it became possible to take the observations from the headquarters. So the headquarters of this facility is down in Waimea, so at a gentle 1,000 feet. And for every location, like the other thing, there's pros and cons. So it was a tremendous amount of fun to be up at 14,000 feet. You stay in something that looks like a dorm facility. I mean, really, it's kind of these monastic rooms with a little single bed and tiny little desk. And then you have dinner or breakfast in basically a cafeteria. And you'd meet your colleagues from all over the world. But the benefit of being down in Waimea is you get to interact much more with the technical staff that are operating and dealing with this telescope on a daily basis. And there are about 100 staff that work down in Waimea, so that improves that interaction. And not surprisingly, soon enough it became possible to observe or collect your data from the campuses. So UCI has a very nice remote observing room, the Evans Remote Observing Room, which is a really important facility because with these facilities, you can bring in many more students into this process of collecting the data. So it becomes you expose many more of your team to this process. My least favorite mode was developed during COVID because we couldn't even come to the on-campus piece. We could do it by Zoom. And we called it pajama mode. And I really came to appreciate how important these nights of observations are for training the students and for brainstorming. It's not always clear. There's cloudy nights, and on those cloudy nights, we do an incredible amount of mentoring and writing of papers and thinking of new ideas. Okay, so there's been an evolution. Today we're back in the remote observing, thank goodness, and thinking a lot about science. Okay, so let's return to the second campaign promise, which has been harder to achieve. The idea that you would like, with these big telescopes, in principle, it affords you the ability to see fine detail. And from my perspective, that's all about seeing stars that are as close to the heart of the galaxy as possible. Okay, so this animation is actually some of the first data sets that shows some of the first data sets that we took and shows the problem. And the problem is the atmosphere. The atmosphere is great for us, allows us to survive here on this planet, but it is a total headache for astronomers who want to see through it. And so if there was no atmosphere, there's about 5 bright stars here, each star would be the size of the smallest structures dancing around and would be rock solid. Instead, we get these bug splat patterns. And to me, it's actually rather profound. This light has been traveling to us for 26,000 years. And in the last 30 microseconds, it gets completely distorted. Okay, so I've spent much of my career thinking about, well, how do we fix this distorting effect of the Earth's atmosphere? Of course, give an astronomer a problem, we get pretty creative. And we've come up with many, many solutions. So one solution is you get above it. And that's certainly the solution of both Hubble Space Telescope and the James Webb Space Telescope. You're above the atmosphere, you don't have to worry about it. I can't believe I'm about to say this, but these telescopes are small compared to Keck. And the power of these telescopes for doing the kind of work that I do goes as the diameter to the 4th power. Because I'm not at the summit of Mauna Kea, I can do the math to figure out how much more powerful these space-based ones, more powerful Keck is than these space-based ones are. So you basically get almost a factor of 100. And you get access to a kind of approach that you couldn't otherwise do. Okay, so you want to work hard. It's worth it to work hard to figure out how to beat the distorting effects of the Earth's atmosphere. This animation demonstrates how powerful, in one way, this is. So if you take a long exposure, those dancing bug splats turn into a blurred image. So in fact, the 5 bright stars are seen on the left. And the little box is focused on where we think the center of the galaxy is. So we're really interested in discovering stars in that region. And so the stars in that little, the inset box that's exploded out are the stars that are going to be the key, the stars of the show, so to speak. So overcoming the first 2 critiques of the first proposal. I should have said there were actually 3. 1, your technique won't work. 2, you won't discover stars. And 3, you won't see them move. Okay, so we've mastered 2. Technique works, and you can definitely see stars. Actually, I'm going to go ahead and show this. It's always like, do you want to show us a picture of yourself in front of the telescope or not? But this is, I shared yesterday, this is like my baby pictures. I feel like this is the first instrument that we used to take these first images. And it is amazing with this facility, right? This is a facility that, when it was constructed, is a $100 million facility. It operates at about 50,000 a night. So that's like $1 a second. So you don't mess around. And it is amazing that, that they let young assistant professors monkey around with the instruments. And that's what we did. We took the existing instrument that was not designed to do this kind of work and adapted it. So it was a hardware inexpensive move, and it's all about the software. How do you figure out what the atmosphere is doing versus, what your underlying, sorry, I'm having a little technical glitch. Okay, here we go. So we were looking at the animation on the left before. So this is the atmosphere that's changing what you see every 1/10 of a second. Okay, so the optics let you see the very small scale. The electronics let you read it out fast. Now we're going to stop this on the left. zoom into the middle part and show you, after we've done our separation of what the atmosphere has done versus what's there, I'm going to show you an animation that shows you what we saw once a year. And you can probably find my favorite star in the galaxy. And you don't need a computer to tell you that it's moving really fast. So that's why we had that euphoric moment, actually after 2 images, one in 95 and one in 96. It's like, oh, there's something interesting there. We took 1 more year of data to make sure we hadn't made a mistake and published our first results. So that was the first hint that there was a supermassive black hole. Oh, well, don't clap yet. I'll happily take the clap, but I'm telling you, it gets really better, a lot better. It gets better for a number of reasons. One technological and one from a science critique that pushes you to do more. I mean, we're very critical of each other, but that's good because it forces us to do better. But here the opportunity is to do better in terms of the technology. And it turns out there are other people in the world who want to look through the atmosphere and up and down that have way more money than we do, and that's the military. So as we were working on trying to figure out how to do this in a more sophisticated, more powerful way with hardware, there was a point in the mid-90s when this technology that was developed for the military was declassified. So then all the astronomers had to do was figure out how to make it work, well, we were pretty far, in our application. And this is an animation that shows a couple miracles that don't actually happen, like the dome going away. But we see the light bouncing off that primary mirror, the mirror at the bottom, off something at the top. And different telescopes have the instruments in different locations. At this one, it's behind the primary mirror. So now we're looking in what's called the adaptive optics instruments. And so this is the more powerful way of correcting for the distortions in the Earth's atmosphere. The key element is in the upper right corner. This is called a deformable mirror. And as you might imagine, it can deform to counteract the distorting effects of the Earth's atmosphere. So now we see it hasn't done its job. You see that bug splat pattern happening all the time. Now we're going to see a representation of light that's been messed up by the atmosphere as these what's called wavefronts that look like Pringles potato chips. And what we want to do is we want to take the crinkle out, and we're going to have the deformable mirror take the opposite shape that the atmosphere is put on and make them look like pancakes. Okay, so you can think of this as like a circus funhouse mirror that makes you look weird. You have the opposite one that makes you look flat again. But you have to do this around 1,000 times a second, at a rate of 1,000 times a second. So you really have to work fast. And you need the mirror to have very light segments. So this is why you don't do it with your primary mirror. Those things, I said that it's segmented, so in principle that would work. But this segmented mirror is about this big and has about 360 little segments that the system can move around. Now, a second part of this incredible technology is you have to create something to look at to tell you how to move that deformable segment. And this is a remarkable fluke of nature. So it turns out that up at 90,000 kilometers, there's this little layer of sodium atoms. The sodium atoms are actually deposited there by meteors coming through the Earth's atmosphere. So when you go camping and look up and see a shooting star, it's not a star. It's one of these meteors that are coming and burning up in the atmosphere. And the structure of the atmosphere just fortuitously traps those atoms up in a relatively thin layer. So we take a laser that's tuned to one of the transitions in the sodium atom and shine it up to that layer. So the fact that you see these yellow lines is just an artifact. It's just the laser light being reflected by local dust. We don't care about that at all, but rather the artificial star that it's creating. Each of these 2 telescopes has an adaptive optics system. This was a night where we had time on both. I felt like I was queen of the Kecks that night. It's like 2 giant laser pointers pointing to where the center of the galaxy is. Oh, and for those of you who do like to look up at night, How do you find the center of the galaxy? Well, you look for a constellation called Sagittarius, which is the teapot, and the teapot pours into the center of the galaxy. So if you want to look, that is on a very large scale, how to find the center of the galaxy. That's not how we find it when we're doing this work, but when we go out and actually observe the sky to appreciate its magnificence, that's how we look at it. Okay, so with all of this, our ability to see those stars. So remember I was showing that video. Now this is an animation of how we've been able to see those stars move over the last 30 years. My favorite star, it's got a name that probably needs a better name. Its name is S02. It's because it was the second closest star to where we thought the heart of the galaxy was at the outset of this experiment. So in other words, you wouldn't have bet on that. It was the tortoise and the hare race. But it goes around every 16 years, and it's been a really important piece of how we've figured out that there's a supermassive black hole. So we've moved from just measuring how fast things move around to actually measuring the individual orbits. Okay, so what does SO2 tell us going around every 16 years? Well, I'm going to show you on this picture where I've drawn a circle, which is the region where we could get the best mass estimators inside before we started this work. And we knew that there was about 4 million times the mass of the sun inside a giant region, like so far beyond the Schwarzschild radius, nobody was talking seriously about a supermassive black hole. There's all sorts of reasons for that. So what has this experiment done for you? It's actually confined that mass to a volume that's a factor of 10 million times smaller. It's gotten you down to the scale of a solar system. So this advances the case for a supermassive black hole by a factor of 10 million. And to get a sense of scale, like think about anything you would like more of. For me, it would be research funding. My kids, it would be their allowance. So that's the jump forward. And in fact, that first 3-year experiment got us the first factor of 1,000. So that was good and exciting. But what as I said, I love is that people came right back and said, there's a whole bunch of ways you could go wrong. And so I just thought, fine, we've got to keep going. And keep going we did, and it just got better. So that now we have the strongest evidence to date for the existence of a supermassive black hole, not only in our own galaxy, but anywhere in the universe. So today, we're no longer going after the question of, is there a supermassive black hole, but rather trying to understand the environment in which it lives. Okay, and I have to share that this aspect of the work is one of the things that I love about science. So with the advanced technology, we could, for the first time, see what kinds of stars we were looking at. And almost every prediction for what you should see around a supermassive black hole was inconsistent with the observations. So, I used to joke, well, actually, I won't joke. It is really like being a kid in a candy shop. I mean, there's so much more to do, and it sent us in just a plethora of different directions. Okay, so just to give you a quick sense of some of the issues and new scientific directions that we're going today, there are 2 predictions that I want to highlight here. One is for old stars, and old stars in this context are 1 billion years old. Okay, so the prediction is there should be tons of them. These stars have had a long time to interact, and they kind of want to be where the life of the party is. That's the supermassive black hole. So the supermassive black hole should just have this strong concentration of old stars who've had a lot of time to wander around it. And that concept is an important concept for how we find black holes in other galaxies. You can't do this kind of work, but you can look for the concentration of light. So that concept, that theoretical concept, is important. And yet, in this animation that we did in collaboration with the Advanced Visualization Lab at the University of Illinois, it's really, to me, wonderful how a good graphic really captures what we've been able to do. The little orbits that I showed you before are really nested close in, and we're zooming much further out. So you can see the kinds of orbits that we're now able to measure. As you move further out, the orbits are longer, so it takes longer to get them, and you need less of the orbit. Okay, but let's look at the old stars. The old stars are the orange stars. There are barely any there. So again, so let's start with what's going on. That's a real puzzle, and it's a real puzzle that creates a dilemma not only for our understanding of the center of the galaxy, where there's just no question there is a supermassive black hole there, but also for our methodology for finding black holes elsewhere. The second prediction is for the young stars, and by young I mean a few million years old, and if you anthropomorphize stars, these stars, compared to the old stars, are like the human gestation period. So they're really just babies. And in order to get star formation to occur, you need big balls of gas and dust to be able to collapse down under their own gravity and form stars. Black holes tend to tear things apart through a process we call spaghettification. It's a very visual description of what's going on. So it's the exact opposite thing of what you need to happen to get young stars to form. So the prediction is you just shouldn't have young stars in this environment that's so hostile to star formation. And yet the young stars are the blue-green things here. They're the dominant things we see. So we name this the paradox of youth. How do you get star formation happening in this region where it just should be completely suppressed? And you can kind of see that there's an organization to some of these young stars, which has provided us with a really important clue to how they might have formed. They might have formed in a disk of gas that had enough density and that maybe made our galaxy look like one of those active galactic nuclei in its youth. In other words, we might have been more active in our youth than we are today. And then there are the pink objects that we didn't even think to make predictions for. And those, I find some of the most interesting objects to try to understand. So there's a lot of work being done here, including the extension of the short period stars, where we're actually on the hunt for dark matter at the center of the galaxy. All right, so this is all about what the Nobel Prize was for. So I thought I would share a little bit of that personal journey in terms of just what that looks like. And although I really want to preface this with, nobody does their work to get a prize. And one should be super careful about taking oneself too seriously, having gotten this recognition. Nonetheless, it was a lot of fun. With this picture, I also want to highlight that the Nobel Prize is curated in a really interesting way. The whole process is actually quite interesting. The typical person who gets a Nobel Prize was first nominated 10 years before they get it. So it's a really long process, and it's a process you're not supposed to know anything about. Okay, so behind the scenes, there are people nominating various scientists from all over the world. And then this committee decides initially not who's going to get it, but what field is going to get it. Like, what's really interesting in this field of physics that's happening? And then there's an inversion of the process where people in the community are asked for this topic, who should be recognized, with the understanding that only 3 people can be recognized. So there's a curation of this prize. And in this case, half the prize went to a theorist, and half of the prize went to 2 competing observational teams. And I have to say, I love the curation, because it really recognized the equal importance of theory and experiment, or observations. And you can kind of hear that in the introduction of the different types of black holes. Sometimes one leads and the other follows through the scientific method, and sometimes the other leads, observations lead, and theory follows. So this prize really captured both. And I'm very grateful that it highlighted the importance competition. So this project has been done competitively with a different group that's been working out of Germany. Been super interesting to grow up, really, because remember I started as an assistant professor in this context of a project that started little, that got bigger and bigger, and was done in its entirety in the face of a different team. I learned a lot about science. I could probably write a book that I will never write about this process. Now, the tradition of the Nobel Prize is that they call you right after they've made the decision. They call you right after they've made the decision in Stockholm, Sweden. So in the US, that means, or at least in California, that means that you get a phone call at 2 in the morning. Okay. And for some reason, I still have a home phone. And if you get a call at 2 in the morning, October 2020, right, think about what was happening in the world October 2020. My first thought was, who's sick, right? That's the world that we lived in. And so it really took me a moment to understand, oh, this is not that kind of call. Then I got an invitation to take part in the press conference that was happening at 3 a.m. It was suggested to me that I might want to think about what I would want to say or not say to the reporters. Of course, what did I do? I went and made a cup of coffee. I was totally asleep. But the first question that a reporter asked me, I will never forget, because I've won other prizes, but this one has a really different relationship with the world. And this reporter asked me, how does it feel to win a Nobel Prize at a moment when science is increasingly under attack, and yet we rely on science to get us out of this pandemic? I'm thinking, no question about astrophysics? Not even physics? So that it's been really an interesting process to try to understand that this prize comes with a lot of opportunity, but a lot of responsibility. So how, as an individual, do you want to wear the mantle of responsibility that it comes with? I'll also share that in there's a celebration that happens December 10th, the anniversary of Nobel's death every year. So in this year of the pandemic, which was really complicated, there was a lot of moving discussion around how this would happen, and that what they wanted was it filmed to be streamed December 10th. So they wanted all these events, celebrations of recipients, to be done around the world. So the original concept was all the US people would go to Washington, D.C. That was, I think, the end of October. Then the thinking in November changed to, well, maybe all the California people will go to San Francisco. And this was supposed to be filmed the Tuesday before December 10th. Friday, California goes into lockdown. So we're not going to San Francisco. And so, people have asked me quite frequently, were you disappointed to get a Nobel Prize during COVID? And of course, my thinking is, how could you possibly be disappointed to get the Nobel Prize? And quite frankly, it was lovely to have positive news during this awful moment for all of us. And in this moment that California went to lockdown, I really also felt the value of community. So this happened, so I called a friend who's the dean of the law school, and she said, let's read the lockdown orders. So we did, and we found the exception for Hollywood to do filming. So it turns out there was a whole process where you could get a permit and film with lots of restrictions. I have kids in private school in LA. There's a lot of people associated with Hollywood in those schools. So quickly I started to try to figure out which parents did I have in my cell phone who I could call. And of course the kids got into the act at this point, pointing me to the right parents. So I called one who basically said, I can pull you a permit. So again, and this is Friday, right before Tuesday. And we got it done, no food, no drinks, no champagne, 2 guests, my kids, and this gentleman who came down from San Francisco to do the ceremony. So this was the ceremony in a backyard, and I was thrilled. 2 years later, so about a year ago, we all got the opportunity to go to Stockholm to participate in this thing that's called Nobel Week. And I have to say, I wasn't disappointed. I didn't even miss it until I got to go. And I didn't miss it. I just got to enjoy it. It was a really incredible, over-the-top week and celebration of science. So this is what the ceremony usually looks like. It's a stage with the king and queen of Sweden, and the king awards you the prize. They did an amazing job of curating this week, which was all about really the 2022 laureates, as it should be, and allowing the former 2 years to partake in the festivities. And to partake in the early part of the week, which was all about public engagement. I mean, it is amazing to go to Stockholm and to see the public enthusiasm and excitement around the prize. I mean, we've just had the Oscars in LA. Like, that's the kind of excitement I'm used to. We value the stars. The idea that scientists could be that celebrated was just unbelievable. But you really see what happens in Stockholm because they send everybody out into the local schools. They send us to the local universities. We gave public talks. We did podcasts. I mean, there's incredible public engagement. If you ever get to go to Stockholm, I highly recommend going to the Nobel Museum, because every Nobel laureate is asked to give an artifact. And that artifact can be anything. It can be personal, it can be professional. So there's a whole array of interesting artifacts that people give. And so there's a moment where you give the museum this, and they record what you have to say. And so I decided to give the first data tape, where we recorded the first measurements for this experiment, and highlighted that, in fact, one of the challenges for doing a project over 30 years is actually the maintenance of the code and the data over this time period. It turns out it's a really hard problem, one that I had not thought about 30 years ago, along with the first sheet, the log sheet, where we wrote down, recorded what we were doing. And in those days, it wasn't recorded electronically. It was recorded by hand. And I have to say, when I went back and looked at this first sheet, it just cracked me up. Because there's a comment line. So we used to comment on a lot of things. So there's a comment that I made with the first frame of data where I said, holy shit. Because I realized how well the project would work. So it was a really exciting moment. So that's in the Nobel Museum for all to see. I had my king and I moment. I got seated next to the king at one of the formal dinners. And these dinners are very formal. You're escorted in by whoever your dinner escort is. So for me, it was the king. And this was, I mean, talk about pressure. Science, no problem. But sitting next to the king and making small talk, not my expertise. So in trying to make small talk, the king every year goes to this ceremony and the 2 dinners. So I asked him, well, what's the most memorable dinner you've been to? I mean, he's been to 50 of them because he's the longest serving king of Sweden there's ever been. And he very politically said, why this one? Because it's the first time I've been seated between 2 female laureates. It's usually the wives. Oh, well played. In terms of the event, it was also best holiday card ever. These are my 2 sons who are now 18 and 23. And then it was a wonderful moment to celebrate with the team. So you get a certain number of guests. So I brought my longtime collaborators, Mark Morris and Eric Becklin, who were in that first picture, along with Professors Tuan Do and Dr. Shoko Sakai. And I think of them as the young guys on this collaboration, and they've been with us for the last at least 10 years. So this has been an incredible journey, and we have so much further to go. So if nothing else, I hope I've convinced you that we have a supermassive black hole at the center of the galaxy, and in fact, we now have more questions than answers. Thanks for your attention.
Wow. Well, thank you so much. That's fantastic, Professor Ghez. If we could turn the lights up a little bit, we have some time for questions. And what we'll do is, if people have questions, I think raise your hand. We do have some microphones, just so I understand. Are we going to bring the microphones to them? Okay. So I'll call on folks and then wait for the microphone, if you don't mind. I've got a question right here on the aisle, right here.
So thank you very much for a wonderful talk. What are the pink stars?
What are the what?
The pink stars in your diagram.
Oh, the pink stars. Okay, so these are things, these are objects where we see them develop what's known as tidal tails. So if you've seen the movie Interstellar, where you have a planet that's very close to the black hole, it's a supermassive black hole, you get a tidal wave. And these tails are like tidal waves that lift off the planet or lift off the stars. And it means that there's a very strong gravitational interaction with the black hole and the surface of the star. And these things have to be about 100 times bigger than anything we predicted to be there. So then the challenge becomes, how do you make really big stars at the center of the galaxy? So my favorite theory for this at the moment is that if you take a binary star, so two pairs of stars that are orbiting around each other, and bring them near a black hole, you get what's called three-body interactions. And those three-body interactions can drive the binary star to merge. And when they merge, they inflate. It's actually like resetting the clocks. They become like, I don't know, the twinkle in the eyes. They're not even in the human gestation period. They're like really at the beginning. But they're enormous. And they stay enormous for roughly 10,000 years. So that when they swing by the black hole, they develop these tails, and then they go away again. And that's really important as a process, because we think this is a process that might help us understand the gravitational wave events that we're seeing with LIGO and Virgo. These are the gravitational wave detectors. And in these things, we see the stellar mass black holes. But these stellar mass black holes are actually much bigger than we thought. And initially, they were happening more frequently than we thought. And this highlights that, in fact, if you think about more of those systems coming from centers of galaxies where binary black holes could be interacting with a supermassive black hole, this process could drive those merger events. Okay, so we're not seeing stellar mass black holes merge, but we're discovering a process that may be really important, not only for the center of the galaxy, but also in this other context. Thanks for your question.
Okay, let's see. Hands up so I can see everybody. Okay, we've got someone up here on the left.
So with the understanding of these massive black holes, what kind of theory does this prove? Like, in terms of theory, I mean like string theory or, yeah, the understanding of how the universe works.
Okay, so one, it demonstrates that supermassive black holes, which we, in our theoretical ideas of how the universe forms and evolve, are really important ingredients. So the experiment proves that they exist. Now, you're getting at what does it tell us about our theories for what explains the physics? And the answer is today, nada. String theory, one of the hopes of string theory was the ability to explain what a black hole is. Hasn't delivered on its promise yet. And one of the things that observers like to go after, and it's definitely one of the things that we're going after today, to look at how gravity works near a supermassive black hole, because what you're fundamentally looking for is the deviation from our current understanding of gravity, and the deviation presumably for what changes at the heart. That's a big hope, that you see the imprint on the outside, but it's a big driver for a lot of people's work. So that's one aspect that we actually are going after.
I think we had a question over here. John?
First of all, I want to thank you for such a wonderful and clarifying discussion and presentation today. It's fascinating. So I'm curious, I mean, I'm a non-astronomer, of course, as you'll tell by this question. How far across is this black hole? How big is it? Is it, I mean, you talk about all this mass going into a tiny little spot.
So, actually, I'll tell you, I'll answer that two different ways.
It has to be in a way that I can understand it. Like
Okay,
miles
that's
or light
my
years.
goal. You can tell me if I
Okay,
pass
thank
the
you.
test. Okay, so the event horizon, so the physical size is infinitesimally small. So we can, but the event horizon, or the Schwarzschild radius, for the black hole that we have at 4 million is about 10 times the radius of the sun.
That's the size of it.
That's the size of that radius.
Of the black hole. Okay.
We have to be careful because it's the event horizon. Because once you get 4 million solar masses down to that scale, gravity wins and forces the object down to the infinitesimally small object. Okay, I'm going to give you another way to think about this. Okay, simple math formula. If you want to measure the size in kilometers, you multiply the mass of the black hole in units of mass of the sun. So for ours, it's 4 million. Multiply it times 3, and you've got it in kilometers.
Okay.
Nice, simple trick.
Okay. One other question with that. What's the future of that star that's going around it every 16 years?
Oh, you know, for the lifetime of that object, it's just going to keep orbiting.
So it's not going to get sucked in?
Nope. So in fact, another thing to think about, and again, you have to assume you know what's at the center of the galaxy to say this. So let's assume we have a reasonable model, and caveated with everything we thought was not correct. Once every 10,000 years, a star will fall in or get disrupted by that black hole. So it's not very often. Yeah.
Thank you.
You're welcome.
Here we go. We've got a hand up straight up here to the right in gray there. And then I think we have a young woman in red. We'll go with her next. So gray now.
Hi, thank you for the talk. How will the detection of gravitational waves impact future research of black hole dynamics?
Okay, so today with the current ground-based gravitational wave detectors, they've succeeded after 40 years of technological development. I mean, that's amazing in itself. Are capable of measuring or detecting the merger of stellar mass black holes. Okay. So I think from the point of the supermassive black holes, what we can learn comes from future observations of space-based gravitational wave detectors or instruments. And the one that's planned today is called LISA. In other words, the mergers are what creates this space-time oscillation. And in terms of the frequency that they create, depends on the mass. So you need much longer baselines to understand the mergers of the supermassive black holes. And the reason that's so particularly interesting is that we think that one of the important ways in which galaxies grow and evolve and that supermassive black holes equivalently grow and evolve, is through the mergers of galaxies, each of which contains a supermassive black hole. And we're really interested in understanding that dynamical process of how the two black holes, well, the two galaxies, come together to form one united galaxy. And in these galaxies, the most massive things sink to the center and will merge. But today, there's a lot of questions associated with how that dynamical process works. So that's one answer to your question.
Thank you.
So I think we have a speaker, a woman who had her hand up in red in the middle here. Yeah, there you go. Right here. Wave your hand. There we go. And unfortunately, this is going to be our last question, but I'll have some comments when she finishes.
Oh boy, I wish I had a more intelligent question. I have like 3 tiny questions. The first one is that based on the visualization, it looks as though the speed of the stars inside of its orbit changes as it approaches the center. Is that okay?
That's actually correct. So the stars are going to get closer at closest approach, and that's a consequence of what's called conservation of angular momentum. So it's the same physics that explains why ice skaters who start with their arms outstretched, spinning slowly, can spin themselves up really fast when their arms come in close. So you can think of the star going from far out to close in, so they go faster. Yes.
And I'm assuming that when you do all of these measurements, you're also accounting for the presumable movement of our star around the center at the same
Oh,
time?
yes, right. You definitely have to correct for the Earth's motion around the sun.
Which is it long enough that it is it variable enough that you feel like it has affected?
Oh, you got to correct for it.
Okay.
Absolutely. And then you also have to correct for the sun's motion or the system's motion around the center of the galaxy. So another term. Yeah.
Okay. So a lot of math.
Yeah, there's a lot of, it's like this looks so simple, but there's a lot of complexity behind the scene. Oh, and I should say, that's why competition is really important. Because there's nothing like another team competing with you, A, to keep you on your toes, and B, to find your mistakes. So while we can talk about competition, in a sense, there's also a collaboration that happens on a long time scale. So we all publish our results. So every publication, you kind of learn what the other guy's doing and how they're going to comment on your last paper. And we also go to conferences, and so you give talks, and there's sort of like a little sneak peek and a little sneak response. So yeah, that's super important in terms of ironing out all the complexities that are underneath the hood.
Thank you so much.
You're welcome. Thanks for your questions.
Okay, everyone, I think we need to give Professor Ghez a little bit of a break, so let's thank her again.
Thank you.